And welcome everybody to today's session. So I have the pleasure today, after a very short welcome, to show you a real-world case study using JMP. As you see, the title of this session is Better Teaching Data Analytics for Material Science. So why a case study? And this is actually coming from one of our customers. So I think that also for teaching it is really important also to use real-world data to show how to solve real-world problems. And this is an excellent example, which I would like to start with just to inspire you to see what you can do by combining different techniques, including multivariate analysis, design of experiments, and predictive modeling into it's a complex but really sophisticated and exciting workflow. So that will be the first case study I would like to present. Afterwards, I would like to show you, as time allows, some more relevant concepts, skills we believe are also relevant for students to know about. And I would like to show you some of these and how to get started in a class, how to use the JMP platforms to introduce these concepts. And finally, I will have some good news about our teaching resources and support coming from the academic program before wrapping up. So that's the plan for today. I don't want to make too many words about JMP, our company, about the software. So you probably already know about that it's coming from SAS. It's 30 years old, actually. And I would say it's the most interactive, visual, and really intuitive package combining all these techniques you need to learn from data or to teach with data. And what I will show you today is just using our point and click interface, but just to let you know that you can also develop applications in JMP using the JMP scripting language, get data from databases, and also extend the JMP functionality by integrating with other packages, including R, Python, MATLAB, and so on. So if you are really new to JMP, you could go to jmp.com, our homepage, and there may be some points to get started. Here on the software tab, you can learn about the main products. By the way, a JMP academic site license also includes JMP Pro, and you can just click here to learn more about JMP Pro specific features. And then on the next tab, JMP in Action, you see our application areas. So here you can learn more about DOE, about quality tools, predictive modeling, data visualization. So I think at least these first 4 areas are relevant for you in material science, and we will touch all of them. Just click on one of these links and you get access to white papers, some demos and use cases. And on the right-hand side, you can learn about customer stories, our customers in industry, but also academic customers using our software in teaching and research. And if you want to learn more about the academic program, so you see this academic tab here. And if you scroll down on our academic landing page, you get access to our free resources and course material, and we will come back to that later after looking at our examples. So let me start with this case here. So this was actually presented by Silvio Miccio from Procter & Gamble, one of our industry customers. And he gave this presentation 2 years ago at our user conference. And many people were really excited about this workflow and what he did. And this example is also available as a Mastering JMP webinar, so you can also see it online. And there you can also get the data. So if you want to follow the same example on your own, just get a your JMP version or a trial version, and you can also do it yourself. So this application is from chemometrics, and it's similar to this QSAR application you are probably familiar with, and it's about a formulation experiment. So here in this experiment you have continuous factors like pressure and temperature and so on, but there's also a selection of raw material which has to be done. And for this there are 45 options, and what you typically do or would do is probably to have one categorical variable with attribute data, with levels, 45 levels, so with candidate 1, candidate 2, candidate 3, and then you test all of them under combinations of all the other conditions just to select the best option, which is the best material to use in this example. So if this is a detergent, then you would maybe measure the cleaning ability, and then you want to maximize this. And we actually have one response we want to maximize, but there's maybe also a side effect we don't want to have, so there's also a second response we want to minimize. But there's something better. There's a better idea than using just one variable with attribute data. And what Procter & Gamble did was to use the properties of the materials instead of just their labels or IDs. So they collected 19 physical, chemical, or biological properties. So here you see some examples of all the 45 materials. And then they created a model based on these properties. And this may sound like an extra step. So why to do this? Why to collect and transform all these properties and get all these data into the data table as well? And why to build a model? Because this helps you also to understand why a material is a good material. So because of some properties which are causing being a material good or not that good. There's another advantage. If new material is coming in, you can just use your model and it will tell you immediately how good that material should be. The model will predict the ability of any new material coming in. You don't need to test again and again. And furthermore, visual thinking. So you can ask, what would be the best material I could imagine? So that means you can use your model and optimize, and this will tell you what the best material would look like. And then maybe you can ask your supplier, give a specification, and just ask for that material. And with all these benefits, in addition, they reduced the overall effort for testing. So they really reduced time and cost on the whole exercise. And there are several applications for what they did, and I would like to introduce you to this data set now. And let's start here. So this is a JMP data table you probably saw before. And in this data table we have the physical, chemical properties of our raw materials. And these are 19 properties from X1 to X19, 19 properties, and they are saved for all our 45 material options. All the materials we have in our sample, we have X1 to X19. These are our inputs, and then we have the two outputs, the responses already measured for these 45 candidates. So we know the responses, and as I mentioned before, y1 should be maximized and y2 should be minimized. So we are not just asking what is the best ID, what is the best material to use. We make the problem a bit bigger at the starting point by looking at these 19 axes. But you will see the first step, and the first step is about reducing the dimensionality again, reducing it back from 19 back to a smaller number of columns, and this is done by principal component analysis. So let me show you. So when you start with these 19 axes, what you would typically do is, hey, we have a multivariate problem. So let's look at all these variables. So I take all 19 variables in here. And then we see the correlations, the numbers, but we also see the pairwise scatter plots. And by shading the ellipses, we can see even better that we have significant correlation in here. So this scatter plot is the relationship between, so this one here again, between x1 and going down x8. So there's a high negative correlation between x1 and x8, and you see that there's also other correlation going on. So this one is x3 and x12, I guess. So there's also there was one categorical factor which was recoded as, I think it's -1 and +1. So you also have to handle this. So now we have only continuous factors, and these are the pairwise scatter plots which point us to high multicollinearity. What you could also do here is we could ask for a color map and also look into outliers, and we will see that later. There's the hotelling t-square which can be used for outlier measurements, and we will come back to that at a later point. But if you think, oh, there's so much correlation going on, so maybe we can reduce the dimensionality here, you could just go from here to stay in the flow, and from multivariate analysis move on to principal component analysis. So I do this, and we get just a light version of the PCA platform you also have in JMP. This is just a starting point, and you can look at a scree plot, and you see, oh, at 5 or 6 it already looks quite good, and you could get a loading plot for 2 dimensions mapping all our input variables. You could also look at a scoring plot mapping all the observations on 2 dimensions. But looking at the eigenvalues, so what we see here is that with just 6 principal components, we explain 85% of the variability in our data. So that's a decision you have to make. So probably everything above 80%, it's quite good, at least for this type of application. That was one of the experiences of our customer, that they say 80% plus is a good value. So 6 is maybe the number of principal components you want to use for further analysis. And then you can just from here save the principal components. You say 6 please, I want to go with 6, and then I would click OK, but they have been saved already before. This is the result you would get: 6 new columns, the principal components, and you see a plus sign, and that means that there is a formula. So these are no static values for our existing 45 materials, this is a formula. So if you would add new materials with all the access, so the principal components would be calculated automatically because there are formulas on all these 6 columns. So this is the full principal component analysis platform. By the way, you see you get bigger graphs and even more options on the red triangle here. Yeah, but we are already done. We have our 6 principal components stored. And if we look at a multivariate analysis again, so I just rerun a saved script I have saved to my data table by clicking this analysis before, just to save some seconds. I just rerun the script and we see this. And if we shade the ellipses again, we see they look much more like round circles. So there's less correlation. You can also see the correlation coefficients here. So there's really less correlation. And as you know, principal components are uncorrelated. So that's as expected, right? So no correlation anymore. And down from 19 to 6 columns. So what can we do with these 6 columns? So we have a reduction in columns now. So the next step is really another reduction, and that's a reduction in rows. So that means we don't want to use all the 45 materials for testing, because if we use an experiment, the experiment can tell us which smaller number, which subsample of materials could also give us a good result to select materials and to build a useful predictive model for material selection. So that's an experiment which comes next. And this is a bit special, a special use of our DOE features, and not the platform is special because this is the custom designer, which is the standard way to design experiments, because this one is the most flexible platform creating optimal designs. But here the only thing we don't need to specify a response. The responses are already in. So the only thing we need to do is we add factors, and as factors we add covariate factors. What does it mean? Typically you add continuous factors or categorical factors, and for continuous you control them. So you set them actively to a low and a high, maybe also to a center value. With covariates, these are factors which are also relevant for our response. So they are also causing a change on the response, but we cannot change them. We cannot control them. That's the basic idea here. And what I do is I choose covariates, and then I pick the 6 principal components. So now we have the principal components chosen as factors, and these are not the low and the highs. These are the values which are already in our data. Yeah, so we cannot control them. We have to take them as they are. And now I continue, and I don't have to worry about modeling and other settings, but JMP suggests to use all the 45 materials, all the rows. And now I reduce this, and that's another decision, a second decision you have to make after the percentage, how much variation to explain with your principal components. This decision is about how many materials, how many rows do we want to take into our experiment? So how big should the subsample of all the materials be? And a good some best practice is probably to say at least 20-25% of the whole sample is a reasonable portion. So we have 45, so I set this to 12 and go with that one. And now I click Make Design, and JMP creates a design. And this takes a few seconds. And now on the design tool in the custom designer, I could make a table, but I actually don't need the table because the result is also shown in my original table with all the 45 rows, because now the 12 selected rows based on the covariate designed experiment, they have been selected. So let me just color them and provide a special marker so that we know which ones are selected. So that's the subsample. So down from 45 rows to 12 rows. And what I do now is from tables, I just take this subset into a new data table. So here we have all the columns, but just for our 12 selected rows. And this is the table which is then used for modeling. And this is a predictive model we are going to build. So predictive, that means we also have to consider validation, cross-validation, so that this model will also be useful on new material, on new data we may get in the future. And remember, if we use the axis and building the model, we will use the axis again, our 19 properties. Remember, they are highly correlated. So that means we should use some proper analysis techniques to do this. And one of these techniques is partial least squares. And to do this, from the Analyze menu, I choose the generic fit model platform, and we have our two responses, and we have all the 19 axes as model effects. So I add them, and then I don't build a multiple regression model using ordinary least squares. Instead, I choose partial least squares. Just go with the default settings. So some other defaults here. So for validation, because we just have a small sample with 12 rows, I choose leave one out for validation. Just keep one out, maybe the first column, the first X. One row, one material, leave one material out, and then measure how good is the model built with all the other materials on that left out row. And then this will be done on all rows and then averaged. So that's the validation technique here. And now I go, and we see this here. The winner is 9, and this is the overview, and we see that using 9 factors from the PLS analysis, going on with 9 latent factors would be the recommended way, the best way to do it. You can also look at the outputs, residuals, diagnostic information, but here this tells us, oh, already the 6 is doing a good job. So maybe it doesn't need to be 9, so 6 is almost that good, has the same quality. So why not trying out the same with 6 factors. So let me go down. So this was the previous one with 9. So now looking at 6 latent factors, looking at the diagnostics. So everything looks quite good. Nothing alarming here. What you typically do is you look at the variation. So here, how do the factors explain our axis, and how do the factors explain the 2 responses? On the responses you see, so y1 is mainly explained by the first factor, which is in red, and y2 is a bit more diverse. So if you are happy with the model with 6 factors, so from here you would choose to save the prediction formula. And this would save the prediction formulas for both responses. And this was already done, so I don't need to do this again. So we already have the prediction formulas in here. So there's one formula for y1 and a second one for y2. These are formulas, so they have a plus sign. And clicking on the plus, you see the equation how to calculate y1 based on all the axes following this PLS model equation. And same for y2. Another option you probably get an idea about, what about generalized regression, and especially with elastic net or ridge regression. This could do a good job. So I just build the same model, same y's and x's, but now I choose generalized regression, which is another option on the personalities in JMP Pro. I run this. So that was just a question. I say no. And then here I change this to elastic net, because this is a combination for both responses, elastic net. This is a combination which does 2 jobs. It has the lasso benefit property to shrink variables to 0, so to reduce the model. But it also has the ridge benefit of ridge regression, which is really helpful in case of multicollinearity. And for validation, I choose the same strategy, leave 1 out. And now I build the model, and you see the first model for y1. These are the terms which are selected, and you see that the lasso also did a good job. So if we look at the expressions here, you see that the expressions are much simpler. The model is much smaller and lighter than the PLS model. Again, if you like this, if you want to keep this, you would also save the prediction formulas from here. So that's the red triangle, and then save formulas, save prediction formulas. By the way, you can also export the scoring code of any model as Python or JavaScript or C code if you want to deploy the model somewhere else and not in JMP. So this was also done. So we have these 2 formulas here. So 2 models and 2 responses, 4 formulas. And then I copied them already back to our original data table with all 45 materials. So here we have the same models I just built and created with a subset, and they are now back, and we see the simple models using elastic net stored on these columns. So that was the model building process, just using 2 options, but they are quite good and dealing with multicollinearity. And now the question is, what is the best material? Can we tell what the best material looks like? And how can we do this? So the tool which could help us here is the JMP profiler. So I start the profiler from the graph menu. I just take the PLS models right now and I say expand the intermediate formulas because I don't want to see the principal components in the profiler. I really want to go down to my properties, the x1 to x19 raw data. Yeah, so I take the two prediction formulas in here and then we see the profiler. I just switch the desirability off for a moment and let me get this down here. Bye. Okay, so this is the profiler and now we see our two responses on the left and we see the mid settings of all our 19 properties or factors. And I can change one setting and we see how this changes both of the responses. So what are the important properties? So this can be easily answered by asking for variable importance, which does some Monte Carlo simulation. So this is not about statistical significance. This is really about the practical importance of our factors. And this also does a sorting of our factors. So the most important one is now on the left and the second is on the next place to the right. We can also colorize the profiler, and the more red a relationship is, the more important it is for that response. So that's one thing, to learn what are the important properties here of our materials regarding our two responses. But then back to our question, what is the best material? So for this, the best in JMP is translated as a desirability. Best means set the materials so that we get the responses we really want. And this is shown here as the desirability for our responses. The first, Y1, that means the higher the better, or maximize, and the other one is the lower the better, or minimize. I could also double click here and you see this is maximize and it sets a desirability. And by that, JMP knows what is good, what do we want, what do we desire. So it means that I can ask for the best desirability, to maximize the desirability. So to set all the factors so that we get the best Y1 and Y2 responses we can think about. What does it mean? Is this the best? Should we use a material like this? So let me append the settings we have now after the optimization. Let me append the settings to our data table. I close the profiler again. So now we got this new row down here with the best settings of our x1 to x19. So I choose another color and marker so that we can identify this best material profile. And then we look, I just run the multivariate scatter plot again. And we see, let me make this a bit bigger. We see the new one. So you see the orange square symbol. Are you happy with that? Would you go with that material? No. So there should be really some concern here, because you see what we did is we are really out of the model space right now. So we did some extrapolation, and we would really have to be lucky that this would be really a good material. So we would be much more on the safe side if our best material is drawn a bit back into our model space. So back to the main cloud of our other material data points. How can we do this? So I already showed you that we can save this hoteling t-square distance from the principal component analysis. And this is actually from the multivariate platform. And the d mod x, that's the distance from the modeling space of our principal components. And this is a distance which can be saved from the PCA platform. And they are both formulas, so that's also important, because if we add new materials, they will be calculated automatically. So now what I do instead is, let me just hide and exclude this one we got as the best, but we are not happy with. I exclude this for now. So back to our 45 data points, and I start another profiler. So the profiler this time with the same prediction formulas, our two models for the two responses, but this time I also add the distances. So I also, oops, that was the wrong button, sorry, graph profiler. So recall, so we have these two, and I need to add the two distances. So first click here. So now we have 4 responses for a global optimization. And I click OK. And now I have to check the desirabilities. So here we have hoteling t-square. And of course, the distance should be minimized. So we want to get closer to our data points, other data points. And that's some experience you should have. So setting the range here. So we really have to try this out to get it more or less close to the other data points. That's some type of experience, but you can just try it out. So I just set a small range here, minimize for the t-square, and also minimize the d mod x, minimize this one, and I go from 1 to 0.9 down to 0.8, and that's it. And now I optimize again, maximize desirability. So this takes a few seconds now. So now we are done, and I append the settings again to the table. So same thing, another material row, and I give this another color and marker so that we can see it. And I do the same thing. Look at the multivariate scatter plots and look at the new guy. Yeah, we got in. So here you see that this is much closer to our main data cloud than before. Much closer. So we would feel much safer and less extrapolation. So going with this best material. So if you could order this type of material and with this specification, just get it. So this is the most promising following our PLS model. But what if we have to pick just one of the available ones. So we cannot just order and get anything we want to see. We just have to use one of the commercially available materials. If that's the case, there are several options to do this. One is using the multidimensional scaling platform, and then we have all the data points, and also the green one here, which is the new optimum, the better optimum. And then we see all the proximities down here, and then I would make this into a new data table. I'm interested in what is the row, the new one, 47. So I select all the matching rows and then make this into a new data table again. Subset, new data table. And then I can look for the closest one to this 47, our winner. So I do some sorting here, and we see the winner is 18. And if I select the 18 down here, so that's the 18 data point. Maybe I change this color again to a purple one. So if we look at the plot, get it back. So we see this is the winner down here. But if you also have some commercial properties, maybe you can also take the second best. Not 18, also 13 should do a good job, or 14. So that's the example I wanted to show you. And let me just tidy up a bit here and close this one. I can show you this right briefly. The last step actually is model comparison. So I think we were done. So we know what is the best material we can think about. That's the winner after the optimization. And then what's the closest, the best material we have on stock. So that's the row 19. So by that, the question is done. I mentioned another benefit. So if new material is coming in, we could also use the model to predict how good that new material would be. So here you may be interested in, how good is it? How good is the model on prediction? So for that you would use some cross-validation techniques and split the data into training and test data. And we already did this. So here you see on the data set, I have to scroll it a bit. So I already have a validation column, and the 12 selected ones from the covariate experiment, these are the training data sets because they were used to build the model. And all the other materials were not used building the model, so they can be used for testing. And then there's a platform on the Analyze menu, Predictive Modeling. It's model comparison. Let me do this. It's quite easy to start it. So I'm interested in these formulas. So I get this output for all my data. So I'm now looking at all the 45 materials. So that includes training and test. So to split it, to only look at the test data, which is a more honest evaluation, I add a local data filter. So the validation, I add this one. And now I can look at the training data and also look at the test data only. So training includes the 12, the subsample 12 materials and test. These are the other 33 which were not used for model building, which are now used for measuring how good the model is on new data, new materials. And here the answers are given for Y1 and Y2. And we see that for both, the PLS model is doing the best job. So you can look at the R-square or errors and other metrics. And I think they're all giving the same answer. So PLS is the best one. But as you see, the generalized regression using elastic net is also doing quite a good job for both responses. So if it's also important for you to have a small, simpler model rather than the full-blown model you got from the PLS analysis, then the generalized regression model could be also an option for you. In any case, with any model, I think the benefits are really convincing. So you can reduce the effort, and this is maybe hard to see from the demo, but imagine in a formulation experiment, you have to test all your materials at all conditions, and these can be many, many combinations. And if you get new material coming in, you have to test it again. With this approach, building a sustainable model, you can keep the model and then just reduce your data, principal components for reducing the columns, then the covariate experiment to reduce the sample from 45 to 12. So that means we only have to test with the 12 materials. And why is this a good idea? Let me also exclude the winner we got. So if we look at the 3D scatter plot, so the 18, that's the purple one, and you see all the star symbols are the ones which were selected by the covariate design experiment. And if you are experienced in DOE, you probably know that testing at the corners, at the border of your design space is a good idea. And this is exactly what came out from this method. So we are really testing at the outside or the outer skin of our cloud here, of the full data cloud, and we don't need to test at all the inner data points and materials. So these are the 12 materials selected by a DOE. And overall, mixing all of this into one workflow shows you all the power also of a software which covers DOE and multivariate analysis and predictive modeling, and of course some visualization everywhere. And you don't need to switch between packages because you have one for visualization, another one for designing experiments. No, it's all in one package and it's all connected. That's another good message here. So that's the end of that case. So maybe I spent a bit more time than planned, but I think this is really eye-opening and inspiring what you can do with modern software today. And I just skip this section here. So these are some other concepts and skills also important. And by the way, we plan to share this journal with you. We will let you know in the follow-up email how you can get it. And then you can also look at these examples and open the data sets. These are all sample data built into JMP. So you can just click them to see an example for designing an experiment. Another example is about exploratory data analysis, quite essential. These are all basic skills, and we have dedicated webinars about these topics. So you can dig deeper into all of these concepts and methods by a dedicated webinar. I think the case I presented had the beauty that it combined all of these into a real world problem and some statistical thinking, which are also used by our customers. So data cleaning, I saw that you were also interested in these topics as well. Please use any search engine or look our webinars, so you will see some examples how to explore outliers and missing values, do imputation. So we have tool sets for these data cleaning tasks as well. And also recoding, which is really cool. You can group similar values together. So this is more for categorical data, where you maybe have manually entered strings, and some of them are not the same but really similar, and they mean the same. So you would like to group them together, and if you have thousands of rows, you don't want to do this manually. So if these are error reports or any comments or measurement reports, you can use them and the tools I just mentioned. Another topic is about quality and process tools, and here it's about understanding variability. And beside designing experiments, I think, and many others think, that understanding variability is the other big skill set you would expect from a data scientist. And JMP has many tools for that as well. So this is about measurement system analysis, and you can just click here, and all these data sets, they have some scripts you can play with. So this is asking about, we have these data here, we are measuring a Y on a gasket. And we have 3 operators, A, B, and C. They are measuring all the 6 parts. And this is the Y they measured. And just by selecting this, you see, oh, the second part has a high Y. So if you want to maximize, that's maybe a good part. So you can just explore the data in various JMP platforms. But platforms like measurement systems analysis really tell you about where the variation is coming from. Is it coming from an operator, or is it really coming from a part? Is it part-to-part variation? And you can look at other outputs. So this output here tells you about interactions. So if all the lines are going in parallel, so that's all good. So then you don't have an interaction between operators and parts, which would mean that different operators get to different results measuring the 6 parts. So you can look into this, and then evaluating the measurement process. That's the modern method here. This is an output about variance components, and you probably know gauge R&R. This is about repeatability and reproducibility, and you can see if this is a problem. But this looks quite good. So this tells us that 94% of the variation in our data is really coming from the products, the parts we are measuring, and not from the operator, or just redoing the same measurement by the same operator, because maybe they are not trained and they are doing this differently every time. So then you would have a repeatability issue. But this looks quite good, and you can get to this quite easily. That's measurement systems analysis, quite often ignored before analyzing any observed data. but quite important, because if the measurement process is not set up properly, you may just look at noise and then you can try to learn something, but it doesn't really make sense. And the last section here is about statistical process control and control charts. And here I just invite you to look at Quality and Process Control Chart Builder. So this is so easy to build control charts. So I am interested in diameter measurements. So I just drop it in here and we get automatically an individual measurement and moving range chart. And this was measured per day. And we have several measurements per day. So now we are averaging, and that means we automatically switch to an X bar chart. And I can ask for, are the machines different or are the operators different? And what about the two phases? Did we get some improvement from phase 1 to phase 2? I would say yes, because the variability was really reduced and the process more stable. So in the first phase there were some warnings here telling you that there were some data points out of control you would need to look into and to investigate. So first step is, after knowing that the measurements are okay, you have to ensure that the process and your measurements are stable. And then you can ask for process capability. So are we really matching with the external requirements with the specification? And that's a task for process screening or process capability. And this can be even done with big data in process monitoring. So you can have thousands of processes like this one here. This is 1,455. And looking at process capabilities, so you can get a quick overview about how good the processes are right now concerning the variation and concerning a shift from the average, from the mean. And then you can also look at the individual processes, and this tells you about non-conformance and all the CPK, PPK, and all the indices, and you have these short-term and long-term or within or overall sigma capabilities. So what you probably know, with very nice visuals. And then finally, process screening to screen thousands of projects. So this is the most interesting one on top, automatically sorted. And then here I can just ask for, hey, show me a control chart for this one. What is going on? Is this unstable? What's happening here? And then again, we can also get an overview with all our processes. And this shows you, are they capable? Are they stable? Or one of these? So the green is definitely the zone where you want to be. And that really helps you, even with hundreds of thousands of processes, to focus on the most important ones. Time is over, so sorry for that. There are even more other techniques in JMP we don't have the time to look into, but they are also built in the same package, and I just invite you to try them out. I mentioned some good news at the end, and this is the good news here. The good news is that with a JMP site license, you get free access to all our teaching resources, including the online resources we have on jmp.com/teach. So that's the portal here. And for instance, if you want to teach DOE, if you think, oh, design experiments, that seems to be a relevant topic, I would like to teach this. Is there any material? Just go to the course collections and then check out courses about DOE. And this gives you access to one-page guides and videos other instructor videos and course material, webinars, textbooks, and more. You can also get course material from SAS. So these are complete training kits our SAS trainers use to train our customers about classic design, about custom design, about mixture designs. So you can get all the material for free. And as I mentioned, with a site license, you also get access to our e-learning courses. And there we also have 2 courses, one about classic, one about custom designs. And they maybe take a student 2 or 2.5 days to work through all the material. They are quite entertaining. They are really engaging with real world problems and examples. And every student can do this self-paced, so on their own, and highly recommended. And with a site license, you get all you can eat access, so unlimited access for all your students, just to align them before they come into your course. Or if they want to learn more after your course, you can just point them to these or any other courses we have online. By the way, there's also a course about measurement systems analysis and many other topics, including multivariate analysis, of course. We also have a selection of books. These are just some recommended books we have. You also find online or in your bookstore. And if you have any questions, please get in touch. So our email is academic@jump.com. There's a trial version, and as I said, you will get an email mentioning the next steps and some links, including the example. And I hope that I could inspire you about an interesting use case of JUMP software in material science, and that I touched different techniques, different concepts for solving one problem in a better way than just following any old school approach. At least our customer Procter & Gamble was quite successful with that. And I think it could be also interesting for students to see what can be done and what is a typical workflow I should expect when I move into industry. So I want to thank you for your interest, for joining us today. And I have to ask Paolo if there are any questions coming in.